Thank you for introduction. Okay, so hi, I'm Kana Moriwaki, a PhD student at the University of Tokyo. So today I would like to talk about our recent work based on this paper shown here. And in this talk, we consider to use OIII line emitters as a probe of galaxy-21cm cross-correlation signal from the early stages of reionization. So let's start. Okay. So as you already know, the biggest problem in the 21cm observation is the bright foreground. And basically we want to remove this foreground. And one way is to use the cross-correlation technique. So because the foreground emissions don't have any correlation with the high-redshift galaxies, we can extract the 21cm cosmological 21cm signal by taking the cross-correlation between this contaminated signal and the distribution of the galaxy at redshift that we are interested in. So this is a basic idea of cross-correlation. So the important question is, what kind of galaxy samples are the best traces to be used for cross-correlation analysis? And I think, and I have already explained, the Lyman alpha emitters are considered to be the most promising traces, and they have already been studied in many works. And also the Lyman alpha emitter surveys have already been done by Super HSC at redshift 6.6 and 7.3. So we are basically prepared to do a cross-correlation analysis. However, actually, it is known that Lyman alpha emitters becomes difficult to detect at higher redshift because the Lyman alpha photons are scattered by neutral hydrogen in the IGM at high redshift when the neutral fraction is very large. And indeed, our previous observation by Kana et al. Shows that the Lyman alpha emissions get increasingly small, increasingly weak at redshift larger than 7 compared to the evolution of the UV emission. So this kind of thing indicate that it may be difficult to use Lyman alpha emitters to study the high redshift reionization. So in this study, we instead consider to use the OIII line emitters. So let me explain why we want to focus on the recent ALMA observations have shown that high redshift galaxies at redshift larger than 7 tend to have a brighter OIII luminosity compared to the local galaxies, which is summarized in this plot. And these are the observations done by ALMA. And using a the high redshift galaxies indeed have a bright OIII luminosity because of their high ionizing parameter and low metallicity. And also, when we consider their wavelengths, those OIII emitters could be like jet LSD and line intensity mapping observation like SPECS or CDIM. So these are basically why we want to focus on the OIII emitters. So in this study, to examine the cross-correlation signal between 21cm and OIII emitters, we use a reionization simulation done by Marius 8. And the details, you can check the details on the poster by Marius 8, which you can check on the Slack. And basically, we use a hydrodynamic simulation, massive black second, and use a radiation transfer curve collage by Xiaodi et al. And actually at high redshift, IgM heating is also important, not only the reionization process. So we include a IgM temperature effects on the 21cm signal. So for example, at redshift 10, it's something like this. And here I show the evolution of 7 and the distribution of OIII emitters. So in this plot, the red and blue region show the emission and absorption of 21cm lines. And these black and red points are the bright OIII emitters. So here to compute the OIII luminosity, we use our own emission line model. But basically, the OIII line emitters the luminosity of OIII luminosity scales with the star formation rate. So basically, we can consider that the OIII emitters is just tracing ionizing sources and heating sources. So basic trend is something like this. At redshift 10, we can observe OIII emitters somewhere like here. Sorry, it's a bit difficult to see, and we observe a positive correlation between 21cm and OIII emitters. This is because of the positive correlation between temperature fluctuation and galaxies. But at lower redshift, as the ionized bubble gets larger and larger, we observe an anti-correlation. And this is a bit because of the anti-correlation between galaxies and neutral fraction. So, okay, this trend is summarized in this plot. And here I show on the top, I show the absolute value of crossbar spectrum. And on the bottom, I show the cross-correlation coefficient. So, and it also shows the sign of the observed signal, sign of the path spectrum. So as we have already seen, at redshift 10, we observe a positive correlation, but at lower redshift, we observe an anti-correlation. So the point here is 0.1 megaparsec inverse. We observe a positive to negative transition, something like this, at redshift somewhere between redshift 10 and 8 in this case. And this turnover redshift, let's call it turnover redshift, could be an indication of the beginning of the reionization. So this is one point we find here in this study. And also here I want to study the effect of heating. To do so, I show the power spectrum when we use a computed IgM temperature in the solid line, and the power spectrum when we assume a saturated heating, or in other words, we ignore this temperature fluctuation time. So as you can see from this plot, even when we don't have a temperature fluctuation, at redshift 10, we observe a positive correlation. And this is actually because there is still a positive correlation between density fluctuation and galaxies. However, the amplitude is very different. So this result shows that, first of all, it shows that it is very important to include heating effect when we want to consider the high redshift cross-correlation analysis. And also it shows that this kind of cross-correlation signals may be used to study not only the reionization process, but also the IgM heating process. So this is the second thing we find in this analysis. And lastly, we evaluate the signal detectability. For this purpose, we assume to use a SK1 low with the 1,000-hour observation. And for OIII emitter survey, we assume this kind of sensitivity and this kind of survey volume.
2 minutes.
And here in this, okay. And here in this plot, the dotted line shows the variance, or in other words, error of the power spectrum. And we find that we can detect the power cross-correlation signal on large scales, even at redshift 10, with these kind of observation. And this sensitivity corresponds to this sensitivity for optical line, and 88 micron OIII line. So one way to perform an OIII emitter survey is to use a JWST observation. So we consider what it would be like when we consider to use a JWST. But unfortunately, we find that it takes a very long time for JWST to perform this 1 square degree survey, because JWST's field of view is not that large. So unfortunately, it's not feasible. So to perform this kind of OIII emitter survey, we may need some other telescope, especially a large single dish telescope. So here I show one example of that kind of telescope. This is a proposed telescope called LAST, which I consider to start observation from early 2030. And this will observe a sub-millimeter to millimeter frequency band corresponding to the OIII 80 micron at redshift larger than 8. So if this kind of telescopes start to work in the future, we can detect the 21 centimeter OIII emitters cross-correlation signal, and we can study a lot of things. So here's a summary. In this talk, we have seen that it is important and also interesting to study impact of IGM heating and high redshift cross-correlation signals. And also, if we can observe a positive to negative turnover, then it would indicate the beginning of the epochal reionization. And here in this plot, I show the evolution of the large scale signal as a function of redshift. So the top panel shows in the case of when we consider to use the OIII emitter survey, and at the bottom, I show the result when we consider to use a OIII line intensity mapping instead of OIII galaxy survey, which I didn't touch in this talk, but okay. And the trend is a bit different, but basic idea is same. In this case, we also be able to observe the positive to negative turnover around same redshift. So this could be a key. This turnover could be a key to study the reionization. And also we find that the large scale, 21 centimeter OIII emitter signals can be detected even at redshift 10 with the future surveys. So if you're interested in my work, please refer to this paper. So thank you for listening.